Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will discuss about valence shell electron pair repulsion theory. It is second part. We have in the previous lecture already discussed about those molecules, shapes of those molecules which are having regular shapes. Means in those molecules around the central atom there are only bond pairs. So any molecule in which around the central atom there are only bond pairs, that is having a regular shape. That regular shape means if there are two bond pairs, then the shape of that molecule is linear. For example, I may mention here this one BeF2. Many more examples are there, so I may mention this one BeF2 CO2. Within these molecules, within this one, beryllium is the central atom. Around central atom there are only two bond pairs, so its shape is regular shape. In case of two bond pairs, that is linear. Similarly, around carbon, within this molecule there are two bond pairs only. They are the two double bonds. We call double bond as a super pair. So that simply means there are only two bond pairs. Those bond pairs will orient themselves in such a fashion such that the overall shape of carbon dioxide molecule is linear. Similarly, if there are three bond pairs, then the shape of that molecule is triangular. For example, we have mentioned this example BF3. There are also many more examples. This one, around aluminum atom, within this molecule there are only three bond pairs, so its shape will be a triangle. Its shape will also be triangular. After that, we will move towards this. Four bond pairs around the central atom, then shape of that molecule will be in the shape of a tetrahedron, will be that molecule present. For example, we have mentioned this example, methane molecule, or even there are many more molecules, carbon tetrachloride, this one, SiH4, many more examples. Within them, around the central atom, there are only bond pairs, so their shape is regular. That shape is a tetrahedron. After that, going towards this one, five bond pairs around the central atom, then the shape of that molecule we call as trigonal bipyramidal. After that, six bond pairs around the central atom, we call that as octahedron. Simply, the shape of that molecule is octahedron. So, this one octahedron in shape. Some examples we have mentioned about this. This one example, PCl5. We have discussed its shape. After that, this one octahedral SF6. So, this one being octahedral. Seven bond pairs may be present around the central atom. The shape is equal to pentagonal bipyramidal. So, shape of that molecule will be pentagonal bipyramid. So, the shape of any molecule having seven bond pairs around the central atom. These are the simple shapes because we cannot go beyond this. This theory is about the shape of simple molecules. In today's lecture, we will consider those molecules in which, in addition to bond pairs, there are also lone pairs. Those lone pairs, they will distort the geometry from this regular behavior. That means if there are three, then this linear geometry will be distorted to some extent. Similarly, if there are three bond pairs and even a lone pair or two lone pairs, geometry will definitely get distorted. In today's topic, we will discuss about those molecules. Let us take some examples and I will illustrate you the formation of the geometry of those molecules. What is the geometry of those molecules? And you will clearly understand the things by practicing on them, because these are the questions mostly asked in entrance examination. So you can remember the pointers. First of all, taking this example, ammonia molecule. This ammonia molecule, within ammonia molecule, nitrogen is the central atom. We know valency of nitrogen is 5. It is having 5 valence electrons in its valence shell. Only 3 are bond pairs. Looking on this, 3 are bonded. So these 3 are bonded. After that, these 3, when bonded, these are 1, 2, and 3 electrons of nitrogen atom. So it is 2 electrons will remain in the form of a lone pair. First of all, 4 pairs. We have to count the geometry just like this. 4 pairs their geometry will be tetrahedral, but they are not all bond pairs. So there occurs some sort of distortion. Now tetrahedron will not be formed. Why? This lone pair is directionless. It is wholly and solely belonging to nitrogen atom. So we have to discard this one. After that, we have to shape up these bond pairs which are bound to nitrogen atom. So overall, the shape of this molecule will be this. This is the shape of a pyramid due to the presence of this lone pair, because it occupies, we know already this point, occupies more space around the center atom. This lone pair will push up these electrons closer, so the bond angle, tetrahedral bond angle, which was equal to 109 degree 28 minutes, that will get reduced. So within this, the bond angle is 107 degree. This is the bond angle within this molecule, and the geometry of this molecule we call as pyramidal. So ammonia is pyramidal in shape. After that, I will move towards this point. I will take this example. Taking the example of water molecule. Oxygen is the central atom within water molecule. Oxygen is having 6 valence electrons. Only 2 are involved in bond formation. This one, taking this one and this one, they are involved in bond formation. After that, counting these two ones, there will remain 2 pairs. So this one has 1 pair and this one has 1 pair. They are the 2 lone pairs. Simply counting the number of electron pairs, I may write just like this. This one bonded and this one bonded. After that, this one has lone pair and this one has lone pair. So these two will not determine shape. They will only distort the geometry of these bond pairs. Overall, 4 pairs we know they are arranged in the form of a tetrahedron. But ignoring these two, this is the shape of water molecule will be just like this. This shape we call as bent shape or V shape. However, due to the presence of 2 lone pairs, the bond angle which was in a tetrahedron, that is equal to 109 degree 28 minutes, that will be somewhat lesser than this. That is now 105 degree. Why 105 degree or not equal to 107 degree as in case of ammonia? Because in case of ammonia, there was only 1 lone pair. 2 lone pairs will occupy more space, so they will push these 2 bond pairs more closer. That is why within this molecule, the bond angle that is even reduced. That means that is even less than 107 degree. The third example which I may mention here, that is this ClF3. We know chlorine is having 7 valence electrons. Among them, 3 are bond pairs looking on this, because there are 3 fluorine atoms. So 3 bond pairs, 4 electrons will remain as 2 lone pairs. These are the 3 bond pairs with 3 fluorine atoms. First of all, I have sketched the geometry, rough idea of the geometry in this fashion. After that, we know 5 pairs will be oriented in space in the form of a trigonal bipyramid shape. But there are 2 lone pairs. We know lone pairs occupy more space. They are always within these examples. If we have only example of 5 pairs, among these 5 pairs, some 1, 2, 3 may be as lone pairs. Then we have to put always those lone pairs on the equatorial position. Why? Equatorial positions, in between 2 equatorial positions, the bond angle is 120 degree. That is more than if we place these lone pairs on axial positions. At axial positions, they will orient 90 degree angle with the bond pairs, then there will be more repulsion. So we have to keep this point in mind. If there are lone pairs within this geometry, 5 pairs, consideration of 5 pairs, if there are 1, 2, 3, that will depend upon the molecule. If there are lone pairs, then we have to put always those lone pairs on equatorial position. So looking to this, I will write here, this is chlorine atom, this one has equatorial position, and this one has equatorial position, this one has equatorial position. After that, this one has axial, this one has axial. So I will put these lone pairs here. These are the two lone pairs. After that, I will put these bond pairs at these positions, because at these positions the repulsion will be minimized. So discarding these two, because they are directionless, they will not give the geometry, they simply destroy the regular geometry. Overall, I can say the shape of molecule is just like this. We call this shape as T shape. Now I will move towards this example. For example, here is this BrF5. This is an example, BrF5. Bromine, we know that is having 7 electrons. Among these 7 electrons, 5 are involved in the bond formation. So in total, there are 5 bond pairs. Simply, I will write here a rough sketch. 5 bond pairs. These are the 5 bond pairs. After that, 7 electrons in total. So 1 pair as a lone pair. In total, there are 6 pairs. You know, they will adopt the geometry of an octahedron. This one has bromine atom. Now, these are the 4 pairs in the form of a square. After that, one above the plane of square, one below the plane of square. So there is 1 pair. Within these pairs, 1 pair is lone pair. I will place that lone pair, for example, here. Then overall shape of this molecule will be this one as square, this one as square. After that, counting this one also, we call this as square pyramid. Square pyramid. So shape of this molecule is square pyramidal. Now moving towards the next example, let us take this one. XEF2 means xenon fluoride, xenon difluoride. We will take the example of this. We know around xenon atom there are 8 electrons. Only 2 are involved in bond formation. 2 are involved in bond formation. For example, this one has bond, this one has bond. So 2 electrons. After that, there will remain 6 electrons. They are in the form of 3 lone pairs. Again, counting the number of pairs, in total there are these 3 lone pairs. This one has bond pair, this one has bond pair. These are the 5 pairs in total. 5 pairs. We know 5 pairs is having the geometry of trigonal bipyramid. This is the shape of 5 bond pairs. Actually, this is the shape of 5 bond pairs. First of all, here are only 2 bond pairs. Now 3 lone pairs. In case of trigonal bipyramid, as mentioned earlier, we keep these equatorial positions. On these equatorial positions, we always keep lone pairs, because by keeping lone pairs in this fashion, the bond angle in between them, that is larger in comparison to if lone pairs are placed on the axial position. So keeping lone pairs here, these are the 3 lone pairs. After that, this one above the plane of triangle, and this one below the plane of triangle. This is the bond pair, that means with fluorine, this one with fluorine. After that, we will discard the shapes of these. This one discarded, this one, this one. Overall, the shape of this molecule is this one, XEF2. That is the linear shape. So this molecule is linear in shape. Similarly, counting the electrons in a similar fashion, these examples, I3 negative, this one, ClF2 negative, this one, just like 3 iodide ions plus negative on them, they are also having the same number of electrons as in xenon F2. So their shapes are also linear. They are also linear in shape. Why? In total, there are 5 pairs. Among these 5 pairs, 3 are the lone pairs. 3 are the lone pairs, 2 as bond pairs. 2 as bond pairs, we have to discard these ones. We have to first of all arrange in total 5 pairs. 5 pairs are arranged in this fashion. 3 lone pairs will be placed at the equatorial position. So after that, ignoring these, then the shape of molecule will be just like this. Central atom here, one bond above the plane of triangle, one bond below the plane of triangle. So these will not determine the shape. They are simply directionless. They are only distorting the shape of molecule. So overall shape is determined by bond pairs. So these two bond pairs, they will be at an angle of 180 degrees with respect to each other. So shape in total will be linear. Now taking this example, SF4. SF4, this sulfur is having 6 valence electrons. Among them we know 4 are involved within bond formation. So this one has bond, this one has bond, this one has bond, and this one. This is the oxygen. After that, one lone pair. Why one lone pair? Because in total 6 electrons. 1, 2, 3, 4, 5, and 6. One will remain as lone pair. These 5, there are again 5 pairs. Again 5 pairs. Now these 5 pairs will orient themselves in space in such a fashion such that a trigonal bipyramid is formed. Trigonal bipyramid, again I will take here this sulfur, this one, and this one, and this one. These are the 5 positions in trigonal bipyramid. Now we know we will keep this lone pair on equatorial position. So keeping this here, keeping the 4 bond pairs within these positions, on these positions. So overall, this one omitted, this one discarded. After that, the shape will be just like this. This one we call as seesaw. So SF4 is in the form of a seesaw, because one position, in total again there are 5 pairs. Among them one is lone pair. 5 pairs will adopt the geometry of trigonal bipyramid. We have to discard one equatorial position occupied by the lone pair within a trigonal bipyramid. The remaining shape is the shape of a seesaw. After that, we will take examples of some ions. For example, this one, NH2 negative ion. This ion. What is the shape of this molecule? I will here put down a formula that will be used in an easy way to determine the shape, to determine the number of pairs, where to place those pairs. By means of this simple trick, it will be easier for us to determine the shape. First of all, I will write this number of electron pairs around the central atom. Electron pairs around the central atom, they are equal to 1/2 of, I will write this 1/2 of number of valence electrons. Number of valence electrons of the central atom. We know central atom is the main within this theory, particularly within this theory. Is on the central atom. Hope that you are knowing. In our consideration there is the central atom. Number of valence electrons of the central atom. If there is negative charge, then we add number of negative charges. Number of negative charges. They will be added. Number of negative charges. If there is positive charge, or there is +2, +1, etc. These can be within this expression. The sign can be taken as minus. So here I will write number of positive charges. Number of positive charges. Number of positive charges. After that, I will write this one plus. Now the number of atoms which are attached to the central atom, they will be also counted within this. I will write the number of atoms attached. Number of atoms attached. Number of atoms attached to the central atom. So we have written this formula. Now counting within this, number of electron pairs around nitrogen atom will be 1/2 of number of valence electrons of nitrogen atom, they are 5, plus there is negative charge, that is of magnitude 1, so plus 1, number of positive charge is not present, so after that number of atoms attached, that is equal to 2, so plus 2. In total that will be 8 divided by 2, that is 4. So there are 4 pairs. 4 pairs. Now we will look on the example. 4 pairs. Within this example, there are only 2 bonds. So among 4 pairs, 2 are bond pairs. Now the remaining 2, they are lone pairs. They are lone pairs. We know 4 pairs are in the form of a tetrahedron, but among them only 2 pairs, they are bonded. They are bonded with 2 hydrogen atoms. This nitrogen atom is bonded with 2 hydrogen atoms. After that, there are 2 lone pairs, this one and this one, just like water molecule. So this is the tetrahedron. First of all, 4 pairs are arranged in the form of a tetrahedron. After that, we will ignore these 2. So shape of this molecule will be again, this will be bent in shape. So bent in shape, this NH2 negative ion is bent in shape. These 2 are the lone pairs. We will write here negative, or we will keep this within this parenthesis. After that, write here negative ion. So overall shape, that is again V shape or bent shape. In this fashion, we can determine shape of any molecule by counting it as lone pairs as well as bond pairs. Let us take this example also. For example, this ion, H3O positive ion. What is the shape of this molecule? So number of electron pairs. First of all, we will count number of electron pairs. Electron pairs is equal to 1/2 of 1/2 of number of electrons on the valence electron or the central atom within this molecule. Central atom within this molecule is oxygen atom, so its valence electrons are 6. After that, a positive charge 1 is there. Positive charge, that means 1 plus is there. So we have to remove that 1. That means that within this expression is taken as -1. After that, counting number of bonded atoms, they are equal to 3 within this example. 3. Again, that is equal to 6 minus 1, 5 plus 3, 8 divided by 2, that is equal to 4. So 4 pairs. Among 4 pairs, we know 3 bond pairs. 3 bond pairs and 1 as lone pair. 1 as lone pair. Overall, 4 pairs, they are in the form of a tetrahedron. In the form of a tetrahedron, but here 1 pair is in the form of a lone pair. So this lone pair, discarding this lone pair contribution it is, so it will only push these bonds close to each other. After that, these 3 pairs are there, so these 3 pairs will be in a shape such that overall pyramid is formed. Means we can say OH3 positive is pyramidal in shape. In this way, by looking on this formula, we can count the bond pairs. Lone pairs means total bond pairs plus lone pairs around the central atom, and it will become easier for us to determine the shape of any molecule, whether that molecule may come in your entrance level examination or your board level examination. You can determine the shape of any simple molecule. Thanks.